Good morning, and thank you for joining today's webinar from Spec Innovations, Cybersecurity and Systems Engineering, Protecting Your Digital Projects. My name is Taylor Duffy, and I will be the moderator for today's webinar. First, I would like to go over some housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the Q&A part of the webinar. You can also interact with us on LinkedIn through the Innoslate Users Group or through X using the handle @Spec Innovations. Now, I would like to introduce you to our guest presenter, Jeff Greer. Jeff Greer is an assistant professor of practice in cybersecurity at the University of North Carolina, Wilmington. When not teaching, he's working on applied R&D projects and is supporting UNCW's Maritime Transportation System Cybersecurity Initiative. The area of interest in Jeff's applied R&D work is the development and application of model-based system of systems cybersecurity engineering, the development of secure enterprise digital operating environments, products, and their production. Previously, Jeff served as Vice President of Operations for a NASDAQ tech company until his retirement in 2018. He's completed technical studies in manufacturing and communication systems engineering. He holds a Master of Science degree in cybersecurity technology. Now I'll hand over the controls to Jeff and we'll get started.
Good morning, everyone. Welcome, and this is going to be a really fun conversation, but we have a lot to cover for the allotted hour here today. So just in terms of agenda, we're going to talk a little bit about cybersecurity, just in a general sense, some background information. We're going to focus on work processes and methods, specifically details on modeling. And then we're going to talk about Innoslate and why it's essential to my work. And then there'll be a question and answer session. Okay, so focusing on background here, let's talk about the system of interest types, right? It's all about everything being digital. You have digital operating environments, digital enterprises, digital value propositions, which is our area of interest here today. Digital production capabilities, digital systems and subsystems, and ultimately digital components if you get down to the microprocessor level. So cybersecurity is essential to all of those. So if we just decompose digital value propositions, there's actually 5 different types. This came from Joe Pine, Experienced Economy, his economic theory of everything. But there's commodities, goods, services, experiences, and transformations. Commodities are things that are grown or extracted from the ground. Goods provide functionality. Services provide convenience. Experiences, they're temporary psychographic rewards, like I'm going to Disney. And then there's transformations, like a permanent change in state. You walk into a hospital sick, you walk out healthy. So the main thing here is these are all, there's either digital technology involved with the value proposition or in its production. So what is cybersecurity? So if we think of a cyber physical system, security occurs when a system of interest is operating normally without operational impairment. Accidents occur when there is a loss of security. The impact of accidents varies by cyber attack type, ranging from the loss of information, CIA, confidentiality, integrity, and availability, to a catastrophic industrial event or a DoD mission failure. Cybersecurity can be defined in 6 words. Protection of digital assets from cyber risk. It's simply the best way to look at this. So I like to take the complex and simplify it for ease of decision making and action. So here's your quick degree program in cybersecurity. I like to teach students that digital technologies come and go, but critical thinking skills are eternal and essential for success. So here's the 5 key questions they need to know how to ask and find answers for. What is it? Why is it important? How does it work? How can it fail? And then how can failure be prevented or managed? So the it is your system of interest. So here's the cybersecurity design challenge. if we think about it, cyber risk management theory is generally known. You know, get a degree in cybersecurity and they'll teach you all about it. And then we have a declared system of interest for creation of a cyber risk management strategy to protect it. So that's generally pretty well known if you're working in that space. What's lesser known is the work process and methods for the application of theory into the domain. So if you think about the 5 questions I just mentioned, how do you prevent failure? Well, that's your cyber risk management theory in Q5 there. If you think about what is it and why is it important, that's your Q1 and Q2. For your, you know, system of interest in its domain, and then how does it work and how can it fail? That's your questions 3 and 4 that you need to address with your work process and methods. So let's just take a minute and just talk about the design engagement. You know, senior cyber risk manager. That's it's an abstraction. It can be any one of a number of titles. Anything from you know, CISO to a security architect to a network engineer, but there's somebody that's responsible for, you know, the managing cyber risk. So you have to think about your use case, you know the players, who are the project sponsors, who's the senior cyber risk manager, design team members, internal stakeholders, external stakeholders. You know, you need to know who all these folks are. And then if you think about use cases, you can conduct a study. It can be a descriptive study, you know, observational, as built, as performing, or it can be an analytical study, which is a conceptual design, specification driven, you know, to accomplish a specific function. So conducting a study is one use case. The other is a new solution design. You know, it's a simple 4-step process. Model, analyze, design, and implement, starting with a white sheet of paper. And then finally, there's existing condition improvement. So for your security domain study, SOI, you can start with a descriptive study, documenting the observational as built, and then you can use an analytical study to develop a conceptual specification-driven new design. What's important in all this is tools, right? And so just going to go through real quickly useful in-a-slate functionality needed for practicing cybersecurity by design. And then as I go through the rest of the presentation, I'll talk even more about that. So here's my list of essential in-a-slate functionality. So first off, you need a collaborative team workspace. Nobody manages cybersecurity individually as an individual contributor. It's a team-based effort. So to the extent you have a collaborative team workspace, everybody can document their work. It's recorded, and anytime you need to go in and look something up, everybody knows where to go find it. The other thing is project management tools. I mean, ultimately, IT infrastructure and cybersecurity gets managed one project at a time. So whether you need the full-blown Gantt chart or just a Kanban task board, you know, all that functionality is in a slate, and it's really useful. The other is the documents repository. Cybersecurity program is based on documents, right? There's security policies. There's all sorts of technical documents. So you need a place to store all your documents. Use case documentation is important as well for any project that you execute. And then, you know, one of the first steps in setting up a project is your requirements capture. So you need to, you know, be able to get those documented, because that's what you'll need when you get to verification and validation. And then modeling tools, right? We're going to talk a lot about modeling today, the different types of models that you can create to help with your solution design. And then there's features in there for verification and validation support, which are really important. And then risk analysis tools, right? Sort of a heat map. So you make sure that you're managing the most critical cyber risk, although the risk analysis tools can be used for looking at project risk as well. Change management, and then also just summary analytics. Like, if you look at we'll talk about this coming up, your security control package that you have deployed. How many security controls do you have deployed? What types are they? What's their intended benefit? That would be an example of summary analytics. So as we go through here, let's look at work processes and methods. In model-based system engineering, sometimes they're referred to as reference architectures, or the object management group, which I think recently just got sold to the folks running the Digital Twin Consortium. They're known as design patterns. So just an important distinction, a work process versus a work method. A work process emphasizes the overall sequence of work required to achieve a targeted outcome, whereas the method focuses on the techniques or procedures to do the work. You need both. So here's a simple 8-step work process for practicing cybersecurity by design. It's modeled on off of Cisco's network design process, but you need to prepare, set up a design team for the project. You need to plan, capture your project requirements, make sure your use case is clear, and then ultimately, when you start driving for the required outputs for the project, model, analyze, and design. Model in this case is going to be a cyber risk management strategy for the declared SOI. And then when you analyze, you're going to look at compliance requirements and risk. And then when you get to the design, it's going to be the cyber risk management strategy for the declared SOI. I have a typo there. When we model this out, we're going to model out the system of interest, and I'll talk about that a little bit more in a minute. My apologies for the typo. And then ultimately, when you go to implement, you're going to need a POEM, plan of action with milestones. You're going to have to operate the SOI and monitor performance, and then optimize as improve, which is where you improve as needed. And we're going to talk a little bit about why operate is important, particularly for large-scale complex systems, as it pertains to V&V. Okay, so here's the interesting part. There's books written on model-based system engineering. There's also books written on cyber risk management strategy. What's missing, from my point of view, are the modeling and analysis methods for practicing cybersecurity by design. So I put together 12 methods that I think are important for this discussion. So the first one is, you need to model out the system of interest. You can't defend something if you can't visualize it and describe it. And the model is we all know, working with them, that they're an abstraction of reality. So we'll talk a little bit about model quality in a minute. But things that we want to model out is the security domain boundary and attack surface structure. We want to look at functionally, how does a motivated threat actor behave? We want to look at digital assets, not at the detail level, but we want to abstract them for decision-making purposes. The other one then that we need to think about, this is really big, is system operational dependencies. They call this SOTA, system operational dependency analysis. How are those assets coupled together, and how do they work? How do they fail? So we'll talk about that. And then system criticality specifications. You can't protect everything at the same level based on the money that you're willing to spend on cybersecurity. So you need to assess which things are more critical than others so you can set your security scopes. And then ultimately, you want to analyze the system of interest contextual risk. You want to look at known threat actor behavior. You also want to look at reasoned cyber hazard loss impact scenarios, things that can happen that haven't been seen yet. Ultimately, you want to look at your system of interest cybersecurity design requirements, and then you want to look at your risk treatment priorities. So there's your model, there's your analyze. Now, if we look at design, you want to look at the cyber risk management strategy for the system of interest. So you have two types of risk that you want to manage. You have strategic cyber risk, that's your cybersecurity program. We'll talk about that in a little bit more detail. And then you have tactical cyber risk, and that's your post-design security control package selection. And then ultimately verification and validation. So here, let's dive into modeling just a little bit. For those that haven't seen this book, I highly recommend it. And it's a system of systems modeling and analysis. All three authors are out of Purdue University. And its relevancy is today, every system of interest is an apex system of systems. Methods are needed for managing the structure, operation, and control of a large-scale, complex, interdependent system of digital systems. So this is, I can't emphasize this enough, system of systems engineering is a little bit more involved than just system engineering. So this book has some really good input. There's a whole chapter just on modeling system of systems, and all sorts of different analytical techniques that you might find useful. So for the declared SOI that we're going to work on, we're going to take a look at two quality requirements. There's the notion of model fidelity and abstraction level, right? So when we think about model fidelity, the SOI model doesn't reflect reality, right? And then when we look at the abstraction level, does the model contain too little or too much detail, right? So one of the key points of, system engineering is you get that holistic SOI viewpoint, right? So when we think about fidelity, we need to match physical reality, and then we need to have a sufficient level of detail based on the abstraction level. So if you have issues with either of those quality criteria, you might experience a decision-making risk if the model is incomplete and or incorrect, right? So it's important to manage the quality of the SOI model. So when we think about system of interest modeling, this one was for an enterprise. I have them for products, but it's a 3-axis model. This came out of a book by Borky and Bradley out at Colorado State University for effective model-based system engineering. But on the vertical axis, that's your functional axis, right? And then the axis projecting out to the front, that's where I model out the enterprise attack surface in this case, or it could be the product attack surface. And then the security domain boundary sits just inside the attack surface. And then the horizontal axis is the attack surface abstraction, right? And the main thing is you can't think of your system of interest statically. You also need to look at it dynamically. You need to understand how the function of in this case, the enterprise, how it can impact the attack surface structure. So for this diagram, I look at enterprise behavior past, present, and future. And this is a really useful approach for cyber risk management strategy design. So let's dive into the methods a little bit in detail. So this is the first method I'd like to bring to your attention. M1 means method 1. For your system of interest, you need to model out your security domain boundary and attack surface structure. And this is what I call the iBox method, the imaginary box method. And this was derived from some work by Edward Bowers, who wrote a book, Specification-Driven Product Design. And he said, hey, look, what you want to do is put an imaginary box around your system of interest. So, here's an example, maritime examples, but you can put a box around the entire ship. You can put a box around just the engine room. You can put a box around a shoreside facility, or you can put a box, around a port with a ship and a crane, if you will. So the nice part about the iBox method is it is infinitely scalable and universally applicable. So you can just scale it to whatever your system of interest is. And when you think about setting up that imaginary box, when you think about the security domain boundary, that's the dark green section in the middle, the impervious external security domain boundary. And then to the outside of that boundary is where your attack surface is located. And then out there in what we call the threatscape, that's where your motivated threat actors reside. And what they're seeking to do is find an exploitable vulnerability so that they can penetrate or pass through the security domain boundary to gain access to the system of interest digital infrastructure. So on the inside of the security domain boundary, you can have other defense in depth features, to help out with if somebody does get through, can you limit their lateral movement? But the point here is, I don't care what you're designing, it has to have a security domain boundary. By definition, NIST says that the security domain boundary is the area that's under the direct control of the senior cyber risk manager. If he doesn't have direct control, then it's external to the security domain boundary. So once you put that box up and you start to think about what can penetrate the box, where are the penetration for staging a cyber attack, right? So, again, analysis criteria, think of the boundary as an impervious surface. What you want to do is identify the vulnerabilities in the boundary, security domain boundary. And by the way, the security domain boundary, there was some work by Boardman and Sauser on security domain boundaries, and it can either be a line, or if you think about a house, the external walls of the house are a security domain boundary for the house, but internal walls of the house, that's where you find your MEP, mechanical, electrical, plumbing, in the wall of the house. So when you think about the security domain boundary for your system of interest, it can be a simple line, or there can be functionality embedded into the security domain boundary itself. So if you study this long enough, for any given security domain boundary, there are 4 potential vulnerability types. And so the vulnerability types are digital, cyber supply chain, authorized people, and illicit motivated threat actors gaining physical access to the system of interest. So what penetrates the box, digitally, it can either be a cable or it can be a wireless communication. If we think about the deliveries of digital equipment to, like, say, a ship, right? It can be a cyber supply chain attack, what they call a Trojan horse attack, or an interdiction attack, where you interdict the shipment of computers going to a ship, you put back doors in them, you deliver them to the ship, and once they're installed, you have a back door in. And then there's authorized people that work in the system of interest. They could be a disgruntled employee, sort of an insider attack, or they could be a victim of a social engineering attack, which is not that uncommon these days, where people are motivated threat actors are forcing them to provide access. And then finally, you always have the illicit motivated threat actor that wants to break in and gain access. So what's important here is the notion of the attack vector versus the access vector. The attack vector is, where is the attack delivered? The access vector is the proximity of the motivated threat actor to the system of interest. So a lot of your digital attacks are done remotely over the internet or through wireless satellite communications. Whereas if you have the person trying to break into the system of interest, then basically they have local, they're working to gain local access, right? So you have to think about both of those. And so ultimately, here's a functional diagram. This came right out of InnoSlate. It's an example of what I use for teaching. But a motivated threat actor needs to penetrate the SOI's security domain boundary before they can stage an attack. So, basically, starting at the top, if they get all the way to the bottom in that red square where it says action on SOI objective, that's where they start staging their cyber attack. So what's the strategy to get through the security domain boundary? So, they need to pick an access vector. We mentioned the four. Do they look at the remote digital access strategy, on-premise access strategy, human access strategy, or supply chain access? Then they start looking for the security domain boundary access point. That's the position that they need to achieve. They're going to encounter level 1 event countermeasures at that security domain boundary to the extent they exist. If they get access, then they can start their action on objectives. If they're denied, they can go back and try again, right? But the point is, they need to get past the security domain boundary to be able to stage an attack. And you need to think the same way as the threat actor does if you're going to defend against them. So the next method that I want to talk about is digital asset discovery and abstraction, right? So it's important to have, for the system of interest, right? It's essential to have a listing of all digital components or systems that exist within the security domain boundary. So once you establish that security domain boundary, then what digital assets exist within it? This is commonly referred to as a digital asset listing. They're all known to be accurate to a degree, but never perfectly accurate. Traditional digital asset listings are maintained as a perpetual inventory balance. Modern digital asset listing applications use collector technology to identify the assets connected to a network in near real time. They tend to be a little more accurate these days. But within that security domain boundary, what are the digital assets? Now, one of the benefits of model-based system engineering is that you can abstract the model and elide or eliminate information that is not essential to your decision making. So there's more information in the digital asset listing than is needed for designing a cyber risk management strategy. So when you think about it, every digital asset, is going to have a serial number, may have a location, and truthfully, you don't need that level of detail when you're designing out your cyber risk management strategy. So you can reduce the list of digital assets down to just the classification of assets, right? You can form classes. And the classes need to be defined such that they align with how tactical security controls will be deployed to the classes of digital assets. And I have an example coming up. And then if you want to think about your security controls, there's NIST SP 800-53 titled Assessing Security and Privacy Controls in Information Systems and Organizations. And that's a complete list of what NIST recommends that you consider for use. So, here we are again. We've got the designer system of interest viewpoint, looking at the entire system of systems, if you will, working to manage the model fidelity, but then the abstraction level, you can move that up or down on that pyramid, and you can add or remove detail based on what you need and don't need, right? So what you really think about is, your security controls package, you're going to deploy them to classes of assets, and then those will ultimately get flowed down to all the assets in that class. And those controls can either be digital controls or physical controls. So you want to work to abstract your model properly. The one other thing I would mention is that when we look at your security controls, A lot of those were designed for IT or information technology. But when you look at OT, operating technology controls, you can use some of the IT security controls, but it also typically includes features for managing what's unique in OT, and that is you don't want a catastrophic accident because industrial systems typically have chemicals, high temperatures, pressures, high electrical fields. So you don't want anything to go bang. So they talk about putting in features for failovers for redundancy, fail safes, for accident prevention, backstops. There's a number of features that they can design in physically that you wouldn't normally find in the IT realm. So just wanted to acknowledge that those are out there. There's this whole thing about convergence between IT and OT in a single digital operating environment. We're seeing that more and more every day. Granted, in fintech, might not be a lot of OT there, but if you start looking at manufacturing, if we look at any of the power generation, water plants, you're going to find that converged environment with both IT and OT. And then finally, we get to method 4. So for your system of interest, now that you've got a security domain boundary, you've identified the assets within it, you've abstracted them down to a level that makes them more reasonable to work with. You want to look at your digital asset dependency, right? What are the coupling mechanisms that take your digital assets and tie them together? So power is an easy one, right? There isn't a digital system around that doesn't work without power, right? You lose power, everything fails. But then some things are interconnected or coupled with networks, although some can be standalone for like real-time embedded systems. You can have integrated applications, sometimes with shared data, and then ultimately there can be a human in the loop that needs to couple some systems. So what's important here when you understand the coupling mechanisms and you're looking at all the assets that are involved is how to understand failure prevention and management strategies, right? So independent failures, something just breaks, it wears out, right? And that's in the electromechanical world. Today, why did it digitally fail, right? Was it from a cyber attack, right? So you can have an independent failure. The main thing is with an independent failure, there's no second or third order effects. So you just have an isolated incident to deal with. But then you have this notion of common cause failure, where if your power goes out, it takes everything out. So that's a big deal. And then also important is the notion of cascading failures, right? One system fails, and because it's coupled with other systems, all of a sudden everything in that chain starts to fail. So you really want to take a hard look and understand your dependency chains. So if you're a motivated threat actor, where do I stage an attack within that dependency chain, right? Is it at the end, like for a ship, maybe you go for the engine controller, or maybe one of the subsystems like lubricating oil for the engine, right? It's oftentimes they're just looking for the easiest short path to stage their attack, depending on their motivation. But so you need to understand cascading failure. And so there's a big push today in cybersecurity. Yes, you'd like to, in the perfect world, resist a cyber attack because your protections are perfect, right? But you also have to think about safety and resiliency, right? You don't want to have an accident, so you need to manage how failure occurs, and then resiliency requires that you recover quickly, from an attack, right? So you have to think about this coupling or interdependency when you start to think about, cybersecurity, safety, and resiliency engineering. Here's method 5, criticality analysis. Some digital components and systems are more critical for security objective achievement than others. So for a ship, for example, they'll have typically 5 generators on board. Loss of power is a big deal. They'll have 2 pair online, or they'll have a pair online. They'll have a pair on standby. And then they have an emergency generator, the generator of last resort for the bridge and the medical suite on board the vessel, for the extreme case that they lose all other power sources. So, you want to take a look at which systems are more important. So as a practical matter, you can't protect your system of interest from all cyber risk. So out of criticality assessment, you establish your security scopes for defining which components or systems should be prioritized over others, right? And this when you get into your risk register and you assess your risk high to low, you say, well, just depends on how they get scored out. We'll talk about this in a minute, but you start with security scope number 1 first. There's a spectrum of criteria for assessing criticality. It varies by organization. Safety of life is 1. Fear of a business extinction event is a second one. The loss of sensitive information can be problematic if you're in an engineering intensive company and you have a large patent portfolio, and the life of a patent, I think, is 17 years. So when you think about the engineering investment to build that portfolio, to think that it could all be leaked out in one data exfiltration event, and then all of a sudden your competitive advantage is gone, that's a big deal. Or you can have just temporary operational impairment, right? Somebody's PC gets a virus and they're offline for a little bit, not being productive. So you just go through and you list out your criteria for assessing criticality. And so the criteria typically represent the different levels of, cyber attack impact, right? Anything from loss of life, business extinction, down to temporary impairment. And there's actually NIST instructional reference 8179, which has a whole process just for criticality analysis that you can refer to. Method 6 would be the cyber-informed known threat modeling and analysis study. What has happened. So there's prior work on threat modeling that I would point you to. There's some excellent work out of Carnegie Mellon, their Software Engineering Institute. They have one paper out there, threat modeling, a summary of available methods. So, there's stride, spoofing, just each one of those letters means something. PASTA, Linden, CVSS, attack trees. There's a number of different threat modeling approaches. And then if you look at your intel sources relative to threats, you have both government and industry sources, and you need to be mindful about the contextual risk that exists outside the security domain boundary, right? Who's out there and what are their motivations? Okay. So here's method 7, consequence driven. It's a reasoned cyber hazard loss analysis. What can happen. So when you think about it, you're gonna want to identify the direct and consequential losses to avoid, right? And then you want to ID the hazards that can be triggered by a cyber attack. Then you want to evaluate the hazard impact, and then you want to assess the impact and assign a criticality score. And basically, you're going to want to rank them high to low. But Just because you haven't seen it historically doesn't mean that it can't happen. So this type of work is well known and has been done for years. It's just the cyber aspect of it. What's the cyber event that can trigger the hazard? So what's interesting is that there's been some prior work done in this area too. I would cite some MIT theory and some MITRE theory. MIT has what they call the System Theoretic Process Analysis for Security. This was developed by Nancy Levinson. She's an expert in safety engineering. One of her students, Bill Williams, Dr. Bill, he applied it to cybersecurity. So there's a website up there. They give away a lot of free information on it. And I think the main thing here is that when you look at this plus the MITRE theory that we're going to talk about here in a minute, is this type of work is done at the system of systems level versus the component or the subsystem level. And so MITRE then has a similar set of tools. It's called TARA, T-A-R-A, and it's threat analysis and remediation assessment. And so you can go look at their methodology, but they have some really good online tools for it as well. So method 8 is elicitation of cybersecurity requirements for your system of interest, right? This work came out of Nancy Mead at Carnegie Mellon University. It was done a while ago, and it was done just for IT, but it's fundamentally still sound. So again, if you're running a project and you want to make sure you get good requirements capture, here's 9 steps that Nancy put together. You want to agree on the definitions. You want to identify your security goals. You want to develop artifacts to support your security requirements definition. You want to perform a risk assessment. You want to select your elucidation techniques. There's different ones that she covers in her article on this topic. Then you capture your security requirements, and then you categorize your requirements as to level, system, software, etc., and whether there are other kinds of constraints. Then you prioritize your requirements, and then you go back through and you review the whole list or inspect it to make sure it's what everybody's agreeing on. But the main thing here is this is typically done as a team effort. And then if you get the requirements captured up front, before you even start to do any design work, you effectively give the designers flexibility to consider what they need to accomplish early on. And what she would argue in her work is that all the bolt-ons, just delay, bolt-on requirements at the end, delay the project schedule. They cause work to be redone, which drives cost. And so, better to deal with security by design at the inception of the project. So I put a link in there. If you look up the SQUARE process, Nancy Mead, you'll find the article. So, there's other requirement sources, that you might want to consider. Organization security policies, government statutory law. You need to be compliant with anything legal. Then there's agency, U.S. government agency regulatory law, like possibly, mandatory reporting requirements for cyber attacks. There's various security standards you might have to, capture. Security guidelines, those would be your risk management frameworks. Whether you use, NIST or ISO 27000, possibly your security baselines. If you've done a capability maturity model analysis on your cybersecurity strategy, you might want to look at where there's room for improvement, and then ultimately security procedures, right? So that gets you down into another level of detail. So method 9 is where you start to look at the elements for risk formation. So I've always liked this diagram because it's really simple, right? you have in the diagram, they just show asset, threat, and vulnerability. But really, the asset has to be desired, right? There's a lot of assets out there. If they're not desired, you'll never experience an attack. If you look at the threat actor, they need to be motivated, right? It's sort of like an alligator laying along the bank of a river. They can be a real threat, but if they're not motivated to come attack you, you don't have to worry about them. So you need a motivated threat actor. And then ultimately, you need an exploitable vulnerability, right? You need a way for the threat actor to get to the desired asset of value. So what is that exploitable vulnerability? So what you do is you get all your risk, right? You enumerate them, you list them out. And then using the heat map shown on the right, and this is built right into Innoslate, this is standard functionality, you can create a risk register, and then for each risk, assign a score based on the likelihood of the risk occurring and the impact potential, right? So if we look at impact, negligible at 1 to catastrophic at 5, and then if we look at the likelihood, impossible, there's a lot of risks that are theoretically possible, but practically aren't realistic, all the way up to frequent. And that's sort of the spectrum of choices you have along the horizontal axis there. But what you want to do is rank your risk high to low by security scope first, and then by impact score. So in my work, I'll do this one risk register for every security scope, making sure that I get the highest level security scopes first. So once you have your risk and everything identified, and you think about your cyber risk management strategy design, it's one of these just right balance requirements that you have to work your way through. So you have a management control plane vertically shown. That's the blue. And that's your cybersecurity program. And that's for managing your strategic cyber risk, right? So your strategic cyber risk occurs when your cybersecurity program is insufficient for security objective achievement. So when you think about this, if you're getting taken down by multiple serial cyber attacks on a routine and frequent basis, well then, hey, your cybersecurity program isn't fit for purpose. So you want to take a hard look at whether your cybersecurity program is under or over designed. You have to think about that. And then horizontally, you have the operating plane, and that's where you deploy your security control package. And when you think about the operating plane, that's where your tactical cyber risk is resident. And your tactical cyber risk occurs when your security controls are insufficient or ineffective, right? So maybe you experienced a cyber attack that you didn't anticipate. It's all about adaptive learning. Do you want to make an adjustment, or do you just want to live with the impact? Or maybe you did anticipate the attack, you have controls deployed, but they didn't work as well as you had hoped, right? But the main point here is you've got just two levers, right? You're either working with a cybersecurity program or you're dealing with the tactical cyber risk management security control package. They're interrelated, right? You'd like to say, well, we'll just talk about one and not the other. But like if you're building your digital product, then what policies in your cybersecurity program extend into manufacturing, right? And then where you get these Internet of Things applications now, where it's a customer-owned device, but it's talking back to your server, where you have application software hosted. You need to take those into consideration, both operationally in terms of and then how you're going to manage the infrastructure on site. So my main point here is you don't do anything without thinking about both. You have to think about your management control plane, your operating plane, and it's everything where you need it to be to help prevent your cyber risk. So most people, if you haven't done one, aren't familiar with cybersecurity program design, in terms of structure and function. This is a framework that I pulled from some folks I know. It's an enterprise cybersecurity framework. And so basically, as I mentioned before, cybersecurity programs are built on policies. So you have to have a complete set of cybersecurity policies. There's whole books just on cybersecurity policy and how to write them. And then when you look at the programmatics, people, budget, and technology, how many people are on the cyber team, how much budget do we have, how are we going to allocate the resources based on, functional areas that we need to cover, ranging from system administration all the way down to incident response. And then finally, there's IT lifecycle management. What's the strategy for that? That's where ITIL, for those that are familiar with it, Information Technology Infrastructure Library for managing IT infrastructure. But what's the strategy? What's the engineering aspect of it? And then how are we going to operate those assets? And then finally, you have to assess how all of that is performing, right? So, you want to think through what your cybersecurity program design looks like. And then for method 11, designing out your security control package, NIST provides 20 different control family options. So what's interesting is I'm not going to dwell on one control family over another, but what I will tell you is I took all of these, the 20 families and all their controls, and I think there's close to 1,000 of them, and I uploaded them into Innoslate as a control type, and then ultimately I can just call them up and assign them to either a vulnerability in the security domain boundary, or I can assign them to a class of digital assets. So this is where I start to take the strategy that I'm developing, and I use the modeling functionality within Innoslate to help document my design. So the controls, access, awareness and training, audit, configuration management. Every one of these controls either impacts the operating plane or the management plane of the enterprise and the system of interest. Here's all 20. So for those that haven't seen these before. And then finally, let's talk a little bit about method 12, verification and validation. Verification, that's just where your as-built SOI conforms to the design specification. Validation is that the SOI design is fit for purpose, right? So verifying the design is pretty straightforward. Validating can become difficult. So it all depends on the size of the system of interest, right? Small SOIs can be tested in a lab under conditions replicating their functional use, right? Other large SOIs cannot be tested under lab conditions because they simply just don't fit in a lab, right? Or you don't have the data to replicate reality. They will need to be validated with reason and observed in operation post-deployment to confirm that they're fit for purpose. So in that case, risk can be managed using small-scale pilot test, or maybe at the system level, or maybe a specific device. But ultimately, you're going to reason the entire system to be fit for purpose. And then once you actually go to test it in a live environment, because you have no other choice, always have a backout plan for when problems are encountered. You don't want to get into something, brick it, and have no way back out quickly. And then you can pick your windows for when you cut things in, and maybe you can stagger them in and make sure one area is working properly before you scale across the entire enterprise. So that's it. I just wanted to get through all of the different, the work process and the methods. And this is like a really high level drive-by view. Each one of these methods you can drill down on, and there's a lot more detail sitting in there. But I was telling Taylor at Spec Innovations that, again, there's all these books on model-based system engineering. You've got all these books on cybersecurity. The gap area that we need to do a better job with is how to apply that theory into the domain where the SOI is resident. And this is where the work process methods and spec innovations, specifically all the functionality in InnoSlate, is helpful for that purpose. So that concludes my presentation.
Thanks, Jeff. If you haven't done so, please send your questions through the panel on the right that pops up after clicking Q&A on the top bar. If you're interested in having our team help protect your projects with InnoSlate's cybersecurity capabilities, contact our sales team. You can reach our team by email at sales@innoslate.com or through our website, specinnovations.com/contact-us. All right, we've received several questions already. We'll answer as many questions as we can before our time is up. Can you populate data into InnoSlate with a digital twin of an SOI?
Yes, you can. So I've actually been building prototype digital twins of an enterprise attack surface, harvesting data that exists within an enterprise. So you need your digital asset listing, which can be readily available with a modern set of tools. Then you need your cyber suppliers to be identified. That can come out of your ERP system, followed by human resource records for the people side of it, and then facilities records. And so you can build a digital twin of that security domain boundary and enterprise attack surface. And then what I'm trying to do is transition cyber risk management strategy design from an episodic, several times a year exercise into a near real-time capability, because the speed and the effectiveness with which you manage that attack surface is instrumental to improving your security posture.
Next question, how will MBSE automation with AI impact InnoSlate use for cybersecurity?
Interesting question. There's a lot of work going on with integration of artificial intelligence into model-based system engineering. And my thought is that the methods and when they get applied and how they get applied, I think there's a use case for agentic AI, right? And I've actually designed out control structures where you have persistent goals, and what you need is the agents to be able to act autonomously towards that goal achievement through decision making. So I see some real potential there going forward. We need data models for agentic AI to reason with, so that we can develop defensive AI capabilities to counter adversarial AI capabilities.
Next question, we may need to add the following to the SDB vulnerabilities list: natural disasters, material failures, or malfunctions, design failures. That might be a follow-up of how do we prioritize/account for enterprise dependencies in systems designs, engineering, and security. Dependencies such as firewalls, directory services, DNS, IPAM, ICAM, transport protocols, etc. These may belong in the M4 slide.
Yeah, so first off, I have this really wonderful bow tie diagram, right? And when you think about threats, they're either environmental or man-made, right? So on the left side, it's all the environmental stuff, right? Your your hurricanes, your floods, your fires. So, when you look at your total risk to an enterprise, it could be any one of those, right? And then you go to the right side and you look at all the man-made threats. Clearly one is active war, the other is a cyber attack, cyber sabotage, whatever you want to call it. And you can work your way down from there. So ultimately, there's actually this guidance on how you take your cyber risk and integrate them into your overarching enterprise risk management program. So cyber risk is just one of many types of risk. So I think that answers the first one. What was the second one? The dependencies, and there was a list of security appliances, I believe.
How do we prioritize / account for enterprise dependencies in systems, designs, engineering, and security? Dependencies such as firewalls, directory services, DNS, IPAM, ICAM, transport protocols, etc. These may belong in the M4 slide.
Yeah, so good question. So there's when you think of that apex system of systems, right? And you think about the things that you need to secure. You can start with NetSec, which is net security, ComSec, which is communication security. I call it the SECs. The SEC's an abbreviation for security. You have AppSec, WebSec. You ultimately need a strategy for managing all the different types of assets that are within the system. And then the relationship between them, what's important there is when something fails, what's the impact, right? What's the second and third order effects of that failure? And how do you want to prevent something that's bad from becoming really bad? So hopefully that provides a little insight on that.
Thanks, Jeff. That looks like all the questions we have for today. If you have any others, feel free to email Jeff or Spec Innovations. As a reminder, we'll be following up with you very soon to send you a link to the recording and the presentation slide deck. Make sure to check out the appendices for this webinar at the end of the slide deck. We hope you can join us for next month's webinar, Real MBSE, the Role of Systems Engineering Across the Lifecycle, with Dr. Stephen Dam on Tuesday, November 18th. Your link to sign up will be in the email that is coming soon to your mailbox with the slides and recording. Next slide. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day, and we hope to see you at our next webinar.